So today we will move on to the issue of time evolution in quantum mechanics. Okay, so we will discuss time evolution in quantum mechanics by introducing the next postulate of quantum mechanics, which according to our number is postulate number 4. This is the postulate that tells you that the time evolution of the wave function of a system is governed by the Schrodinger equation. The Schrodinger equation is given by IH bar d psi dt equals h psi. So this is the statement of this postulate. We will now understand what this postulate means. Now, the goal of any physical observation or physical experiment is to try and see how a system changes with respect to time, right? So for example, in classical mechanics, if you have a particle acted upon by some force, you want to understand how the particle moves under this force, right? So you want to understand how its trajectory is with respect to time. So you want to sketch r as a function of t, and that is the job of Newton's second law. Newton's second law tells you that the force is equal to the time rate of change of momentum, which is equal to m times d square r over dt square. So given an initial position, Newton's law tells you how to calculate any other subsequent position of the particle moving under the influence of some force F. So the quantum mechanical equivalent of Newton's second law is postulate number 4 that tells you, given an initial state of the system, given an initial wave function of a system psi of any system upon which some force F is acting, what is the wave function of the system after some time has elapsed? Okay, given psi at time t equal to 0, how do you calculate psi at time t equal to 5 seconds? The answer is given by solving the Schrodinger equation. Schrodinger equation tells you the time rate of change of the wave function psi. So the left-hand side of this equation is the time rate of change of the wave function psi, and the right-hand side of this equation is, is the Hamiltonian operator h acting on the wave function psi. Okay, so what is the Hamiltonian operator? We have already introduced or mentioned what the Hamiltonian operator is in quantum mechanics. The Hamiltonian operator is basically the total energy operator, the kinetic energy plus the potential energy operator. So this is equal to p square over 2m plus v of position operator. Okay. So given a potential energy V of x, I can construct the Hamiltonian for the system by simply adding the potential energy contribution with the kinetic energy contribution. Okay, so this is the total energy operator or the Hamiltonian operator of the system. So for example, okay, so let us take the case of simple harmonic oscillator. In classical mechanics, the simple harmonic oscillator, the total energy of the simple harmonic oscillator E equals 1/2 mv square, the kinetic energy, or equivalently p square over 2m plus 1/2 m omega square x square. And in quantum mechanics, this converts into a Hamiltonian of the simple harmonic oscillator, which is equal to the kinetic energy part remains the same, plus 1/2 m omega square x hat square, where x becomes the position operator x hat. Okay, so that is how you take the classical case and make a corresponding quantum mechanical Hamiltonian out of it. Okay, so let us not go into specific potentials. So let us say that there is some force which is derived from some potential as f equals minus dv over dx, and we have a corresponding potential energy function v of x. and we are still considering only one spatial dimension x, and this is our equation of motion. So written out in all its glory, the time dependent Schrodinger equation is given by IH bar d psi dt equals minus h bar square over 2m d square psi over dx squared plus v of x psi. Okay, notice that in the second equation, I have not written v of x hat because v of x acting on psi would give you v of x times psi. So I'll box this equation because this is an important equation. And this equation is known as the time-dependent Schrodinger equation. Okay, TDSE. So our job is to find out solutions of this equation to understand how the wave function of any quantum system changes with time. Now, you might be tempted to think that the only way you can solve this differential equation, this is a second order differential equation. This is also a partial differential equation because psi depends on both. Psi is a function of both x and t. Okay, so it depends on two different variables. So there is two different, there's partial derivatives here. The only way you can solve this is if we are given the potential v of x. Now, I'm also going to assume at this point in this course that the potential v of x has no time dependence in it. Okay, there is a specific way of solving time dependent potentials in quantum mechanics, but we will not cover that part of this course. So we'll simply assume that all potentials are time independent. All right. So yes, I mean, to understand the solutions, we would need the explicit form of the potential, but surprisingly, we can learn a lot by trying to solve this equation by assuming some general potential. The way we would arrive at a general solution is by using our friend, the separable method. Solution using the variable separable method. Now, we talked about the separable method in the electrodynamics part of the course. So basically, the separable method hinges on the fact that I can write the solution psi of x comma t as a product of two functions, let us say psi of x and phi of t, where psi depends only on x and phi depends only on t. Okay, so the left-hand side is capital psi and the right-hand side is small psi. Now, what gives me the right to do this? What gives me the right to do this is the fact that we are dealing with a linear second order differential equation. So suppose if you have two solutions, any linear combination of the two solutions is also a solution. So I can find out all such psi's and phi's using the separable solution, and I can construct the general solution as a linear combination of all these separable solutions, with some coefficient Cn, psi n of x, phi n of t. Okay, so all I need to do is to try and understand what these individual psi and phi are, and using these I can construct a general linear combination, and the general linear combination is a solution of the time-dependent Schrodinger equation. So my job to solve this general second order differential equation is, so if I call this equation 1, I'll plug in Onsors 2 in equation 1 and try to get simpler equations for psi and phi themselves. So this is very similar in spirit to how we solved the Laplace equation in the first part of this course. So let us actually work out what is d psi dt and what is d psi dx. Remember that psi is a function of psi of x and phi of t. So d psi dt is simply psi of x times d phi dt. Okay, now look at this equation carefully. This tells you that the partial derivative of psi with respect to t is simply psi times the total derivative of phi with respect to t. There is no partial derivative on the right hand side because phi is only a function of time. It has nothing about space. Similarly, d psi dx would be phi of t times d psi dx. And trivially speaking, d squared psi over dt square, sorry, d square psi over dx square would be again phi of t times d square psi over dx square. Okay, so plugging in these things in the time-dependent Schrodinger equation, the time-dependent Schrodinger equation with this onsorts of separable solution would give me IH bar psi of x d phi dt equals, now the potential energy operator is minus IH bar ddx. So this is minus h bar square over 2m phi of t d square psi over dx square. That comes from this part, the first part of this equation, the kinetic energy part, plus v of x times capital psi, which is nothing but psi of x times phi of t. Okay, so this is my time-dependent Schrodinger equation. Now I will divide this equation, divide throughout by capital psi, which is nothing but psi times phi. If I divide this equation by psi times phi, what do I get? The left-hand side, the psi goes away. So I get IH bar 1 over phi of t d phi dt equals, the first term, the psi goes away. Of course, I cannot get rid of the psi because it's appearing in the d square side over dx square part. So this becomes minus h bar square over 2n 1 over psi of x d square psi over dx square. And in the second part, both psi and phi go away. So I only get v of x. Okay, all right. Now let us look at this equation a little more carefully. If you look at this equation carefully, what the division by psi times phi has accomplished for us is that it has separated this equation into a left-hand side equal to right-hand side, where the left-hand side is a function of time alone. Function of time only. And the right-hand side has no t in it. It is a function of x only. Right? So how can a function of time only be equal to something that is a function of position only? Because if I change t, the left-hand side varies, the right-hand side remains a constant. If I change x, the right-hand side varies, but the left-hand side remains a constant. So the only way the left-hand side is equal to right-hand side for all x and t is if the left-hand side and the right-hand side are both by themselves constant. So let's call this constant some e. Okay, so the left-hand side, which is equal to IH bar 1 over phi of t d phi dt, I'll call some e. Okay, I'll call this equation 3. And the right-hand side, sorry, right-hand side, yeah, which is minus h bar square over 2m 1 over psi of x d square psi dx square plus v of x is equal to the same constant e. Remember, it has to be the same constant because the left-hand side and the right-hand side are the same. So they have to be individually constants. And this constant I'm calling e suggestively. There is a reason why I'm calling it. So notice that now, unlike the initial Schrodinger equation, which was a partial differential equation in two variables x and t, the variable separable method has given us two differential equations, but total differential equations in first one in t and the second one in x. In fact, it's even simpler because the first equation, which is a function of t alone, is only a first order differential equation that we can very easily solve. Solve one. What is this? IH bar 1 over phi of t d phi dt equals e. This is equation 3. I can rearrange this to make it look like d phi dt equals E over IH bar phi of t. And if I multiply the numerator and denominator by I get minus IE over H bar times phi of t. Okay? This is a very simple differential equation to solve. So the solution is very simple. So I take the phi in the denominator equals minus IE over H bar times dt. And now I integrate both sides. If I integrate both sides on the left hand side, I get logarithm phi equals minus IE over H bar times t. And the solution of this is nothing but phi of t equals some a e to the minus IE over H bar times t. Okay. So the time dependence is actually quite easily obtained once you put in the variable separable form. The time dependence is simply oscillatory. Okay. All right. So we have solved for the time dependence. What about the other equation? The other equation we cannot solve unless we know the form of the potential energy V of x. So the other equation, which is minus h bar square over 2m 1 over psi d square psi over dx square plus v of x equals e. Excuse me. Notice that I can rearrange this equation into minus h bar square over 2m d square over dx square psi plus v of x psi equals e psi. I just multiplied the word by psi. Okay. So this is nothing but minus h bar square over 2m d square over dx square plus v of x acting on psi equals e times psi. And this equation is the equation that you have to solve to get how the wave function changes with respect to the position x. And this equation is called the time independent Schrodinger equation. TISE. So notice that what we have established right now is that if the potential is time independent, which is what we will assume in this course, then the time dependence of the wave function is always given by a e to the minus IE over h bar times t for separable, for each one of the separable solutions. And the solution with respect to x you can only obtain if you solve the time independent Schrodinger equation. So notice that whatever is inside the square bracket is nothing but the Hamiltonian h. Okay, so the time independent Schrodinger equation is also an eigenvalue equation for the Hamiltonian, because I can write this as h times psi is e times psi. Okay, so the time independent Schrodinger equation is nothing but the eigenvalue problem of the Hamiltonian operator. Okay, so viewed this way, all one has to do is solve an eigenvalue equation. Once you solve the eigenvalue equation, you get the spatial dependence part. Okay, so solving the Schrodinger time dependent Schrodinger equation using the variable separable technique tells us the spatial dependence is oscillatory a e to the minus IE over h bar, and the spatial part can be solved by solving the time independent Schrodinger equation. So assuming that you have all these phi of t's and psi of x's, you can construct the general solution by taking a linear combination of all these n's. What are these n's? These n's simply correspond to different values of the constant E. Okay. Now, as you can clearly guess, the constant E is nothing but the energy of the system. Okay. The system can exist in many different energy states, each one with specific psi n and phi n. And you take a linear combination of all these psi n's and phi n's, and this gives you the general solution to the time dependent Schrodinger equation. Okay, so notice very carefully that even though uh, each one of these states for the separable solutions have a very simple time dependence, the general solution will not have a very simple time dependence, and this is because of interference effects. Let's consider a very simple case. Okay, let's imagine that there is a state, the quantum system with two states, psi1 and psi2, corresponding to energies E1 and E2. Okay, so the general solution is a linear combination of the specific solutions. What is this? The specific solutions are some C1, psi1 of x, a e to the minus I, E1t over h bar, plus C2, psi2 of x, e to the minus I, E2t over h bar. So this is a system with two different energies, E1 and energy states E1 and E2, and the most general solution is a linear combination of the specific solutions for E1 and E2 with separable solutions psi1 phi1 and psi2 phi2. Notice that I cannot decompose these two into something that looks like e to the IET. Even though individually there is an e to the IET, together there is no overall oscillatory nature. What this means is that suppose if I want to calculate the probability of finding the system between x and x plus dx at any time t, then what is this probability? The probability is c1 square, psi1 square, right, times e to the minus ie1t over h bar times e to the plus ie1t over h bar. So psi star psi, that goes away, plus c2 square, psi2 square, plus an interference term, right? C1, C2 times psi1 star psi2, all those things, times e to the I E1 minus E2 t over h bar. There is an interference term in the probability, okay? So this interference term is again a telltale quantum mechanical interference, or a cross term, whatever it is. So in the calculation of probabilities, when you consider general linear combination of states, you should be very careful to include also the cross term here. Okay. So this is the general approach to setting up the solution of the Schrodinger equation, the general solution of the Schrodinger equation. It is very similar to what we did for the electrodynamics differential equations. Simply assume a separable solution and take into account the linearity of the theory. If psi1 and psi2 are solutions, then a psi1 plus b psi2 is also a solution. So once you know all the separable solutions, take a general linear combination of all the separable solutions, and that will be the most general solution. Okay. All right. So this is the general solution. Psi of x comma t is n Cn psi n of x, phi n of t, which is minus I E n t over h bar. Right? So each of these guys can have a different n, basically. So this is what we have as the general solution of the solution of a time-dependent Schrodinger equation. Now, in order to this is how far we can go if we don't know anything about the potential. Once we know what the potential is, we can solve for the psi n of x2 by solving the time-independent Schrodinger equation. Each one of these solutions, psi n e to the minus I e n, the ones that we get using the variable separable method, each one of these solutions is actually called a stationary state. Okay. Now this name can be a little misleading. So obviously stationary means that nothing is changing with respect to time, but that is not obviously true. Each one of these states does have an explicit time dependence, right? They change as e to the minus IENT over h bar. So the reason they are called stationary states is not because they don't change with respect to time, they do, but in these states, all probabilities and expectation values are time independent. So what does this mean? So consider each one of these stationary states, okay? Let us consider a specific psi n, which is equal to some Cn, or I don't even need the Cn in this case. I'll consider this as some uh, psi n of x, excuse me, e to the minus I E n t over h bar, okay? So let us say that I'm preparing the system in this particular state. I'm calculating the expectation value of some operator O or A. So let us calculate the expectation value of some operator A. Okay. What is the definition? I should take the integration of psi n star, sandwich the operator between psi n star and psi n, and take the integration. Right? Now I'll assume that the operator is time independent, okay, which is true for most of the operators that we would be dealing with. A itself has no explicit time dependence, so I can write this guy as psi n star is nothing but little psi n star times e to the plus IENT over h bar A psi n e to the IENT over h bar dx. Okay. Now, if A does not have any weird time dependence like ddt, etc., that can act on the exponential function, if assuming that A does not have any such time dependence, I can take out this e to the IENT over h bar on the right hand side and multiply it with the minus IENT over h bar and multiplied with the plus e to the IENT over h bar, and this just gives me 1. So this is nothing but psi n star A psi n dx. Now, what is psi n star A psi n dx? So remember that this is the expectation value of A at some time t. And this turns out to be equal to, because I did not assume anything about the time in this part, so it is some time t. But this is nothing but psi n star A psi n dx, which is nothing but the expectation value of A at time t equal to 0. Because if I put time t equal to 0, psi n is nothing but little psi n. All the exponential part goes away, that's just 1. So what I have here is basically the expectation value of A at time t equal to 0. So the expectation value of A at some time t is the same as the expectation value of A at time t equal to 0, which means the expectation value of the observable A does not change with respect to time in these states psi n. So this is why these psi n's are called stationary states. Remember, the probability density in the stationary state is nothing but psi n mod square, which is mod of psi n of x times e to the minus IENT over h bar square. This is nothing but mod psi n square. There is no time dependence in the probability. So, okay, so not probabilities and expectation values in each one of these separable states does not change with respect to time, but the probabilities and expectation values in the general state psi, which is a linear combination of all the different separable solutions, do change with respect to time. Okay, it is only the property of the stationary states. Each one of the solutions, the psi n's and the phi n, corresponding to the solution of equations 3 and equation 4, those have the nice property that the expectation values and probabilities in those states do not change. Okay. So this is the definition of a stationary state. A stationary state is one that has an oscillatory time dependence like e to the minus IENT over h bar. And given the specific nature of the time dependence, if you take the combination psi star psi, all the exponential factor goes away. So the expectation value of operators and the probability densities in these states do not change with respect to time. But the most important thing is the general solution to the time-dependent Schrodinger equation, which is a linear combination of all the separable solutions, does have non-trivial time dependences. To get the general solution, one needs to understand how to calculate this psi n's, because the phi n's we have already calculated. They're just e to the minus I in t over h bar. And to do this, we have to know how to solve the time independent Schrodinger equation, which is an eigenvalue equation for the Hamiltonian operator, hi equal to E sub. Okay, so this is nothing but minus h bar square over 2m d square psi over dx square plus v of x psi equals e times psi. So the goal of trying to solve for the wave functions in a quantum mechanical system is to solve the time independent Schrodinger equation, get the spatial dependence, and simply construct the linear combination as given in equation 5 for every specific energy eigenvalue En. Suppose if this eigenvalue equation has 15 different eigenvalues and eigenfunctions, this sum would be sum over n equal to 1 to 15 of Cn sin of x e to the minus I e n t over h bar, and so on and so forth. Okay, so the goal is to take very simple examples and tell you how to calculate these psi of x's, how to solve the time independent Schrodinger equation, and then how to construct the most general solution in these cases, and then to calculate some simple probabilities and things like that for all these different cases. So this is the solution of the general time dependent Schrodinger equation problem. And in the next module, we will go on to the subject of how to solve for the wave functions in a very simple case of a particle in a box. Okay, so this is something that we have seen before. So we will actually explicitly demonstrate what the wave functions are by solving this equation for the particle in a box scenario. So for now, we will stop.